Hi, my name is Dr. Habib Ahmed, and today my job is to set a look at the inclusion of a new material in Silvaco TCAD software. So let me run the interactive environment for Silvaco TCAD, which is deck build. Here, if we go to commands and then click on structure, then region, click on add region, and then if we click on material, we have a comprehensive list of built-in materials in Silvaco TCAD. Here we see silicon, indium arsenide, scandium nitride, gallium nitride, aluminum nitride, gallium phosphide, etc. So many materials over here. However, Silvaco TCAD does not have all materials that we might need for our research purpose. For example, one of my students is working on copper oxide based photodetectors, and copper oxide is not a built-in material in Silvaco TCAD. So today we will learn how to introduce a new material in Silvaco TCAD. And with that goal in mind, the way forward is that first I will make this structure which is based on silicon, which is the orange layer, and then gallium nitride, which is this layer. And we know that both silicon and gallium nitride are built-in materials in Silvaco TCAD. So first we will make this structure which is 1 micrometer in the x direction and 1 micrometer in the y direction. So we are going to work on a work area of 1 micrometer by 1 micrometer. And we know that in Silvaco TCAD, the downwards direction is the positive y-axis. So after we build this known structure, this structure which is based on default materials in Silvaco TCAD, we will look at different parameters. We will look at the energy band diagram of this structure, the doping concentrations present in this structure, the conduction and valence energy levels, and the quasi-Fermi levels of this structure. And then we will move forward to the inclusion of copper oxide. We will replace silicon with copper oxide, which is copper oxide, as you know, is a new material. It is not a built-in material in Silvaco TCAD. So then I will replace copper oxide over here in place of silicon, and we will look at different parameters of copper oxide deposited on gallium nitride. We will look at the energy band gap, the conduction valence energy levels, and the doping energy levels, the doping concentrations, etc. for the new structure. So with that plan in mind, let me run the Silvaco TCAD environment. So we write down go ATLAS, and somewhere at the end we will write quit, which is used for quitting the code. In between, the first thing that we do in Silvaco TCAD is that we introduce meshing. Meshing are horizontal and vertical lines, and the intersecting points of these lines is called nodes. Like as you can see over here, there are so many different nodes in this structure. And Silvaco TCAD actually introduces different models which is based on the equations of physics, and all these equations are actually simulated at these nodes in our structure, which is introduced by meshing. So we define denser meshing at interfaces or in regions which are more critical to our structure. Like for example, if we are working on light emitting diode, we know that in light emitting diode, the active layer is around 3 to 5 nanometers, really thin. So our plan should be to introduce denser meshing in more critical layers, like in the active layer in light emitting diode, and less dense meshing in regions which are not that much critical, like for example in bulk regions. Now in this structure, our interface is around 0.5 micrometers in the y direction. So we will introduce denser meshing around 0.5 micrometers and less dense meshing in the regions away from the interface. For introduce meshing, we go to commands, and by the way, there are two options. We can click on this option which would define meshing, but this option is used for Athena. It is not used for ATLAS, and today we are going to perform the entire simulation in ATLAS module of Silvaco TCAD software. So we will not define the meshing with Athena. If you define meshing with Athena, it's going to give you error after you run the simulation. So instead of that, we go to structure and then we click on mesh, construct new mesh. And as you know that our structure is running from 0 to 1 in the x direction, so I will define different locations and spacings from 0 to 1 micrometers first for the x direction and then later for the y direction. So assume that our first point is 0, 0, and I'm going to introduce a spacing of 0.05 at this point. Then the next point would be 0.5, which is the interface of the two layers that we are going to construct. And since this interface is critical, so I'm going to introduce a fine meshing at this point 0.005. By the way, the units in Silvaco TCAD by default are micrometers. So this is 0.005 micrometers or 5 nanometers of meshing. Click insert. Then our third point in x direction is 1. And I'm gonna use a spacing of 0.05 over here. Similarly, we will do the same for the y coordinates as well. At 0, 0, I'm going to introduce a meshing as 0.05. At 0.5, which is more critical, it is the interface of the two layers. I'm going to introduce a spacing of 0.005. And then at 1 micrometer, I'm going to reduce this spacing to 0.05 once again. We click on insert and we click on write. So now that the meshing part is done, we have two regions in our structure. So one by one, I'm going to introduce both these regions. Like for example, the first region is gallium nitride, running from 0.5 to 1 micrometer. So for that purpose, I'm going to type these commands. Region number 1, our material is gallium nitride, and then we define different coordinates for that purpose. In x direction, our minimum coordinate is 0 and our maximum coordinate is 1. Similarly, in y direction, this layer of gallium nitride is running from 0.5 micrometers to 1 micrometer. Similarly, we define region number 2. So I'm not going to type it entirely from scratch, and I'm just gonna copy it and then edit it. Region number 2, our material is silicon, running from 0 to 1 micrometer in the x direction and from 0 to 0.5 micrometers in the y direction. Then I will define doping as well for these two regions. For both regions, I will introduce uniform doping. Region number 1, let us assume that our region number 1 is gallium nitride and assume that this is N-type. And its carrier concentration, we can set it to 5 into 10 to the power of 18 per centimeter cube. Similarly, for region number 2, let me set it to P-type, and I'm gonna set the carrier concentration, the whole concentration of region number 2 to 1 into 10 to the power of 18 per centimeter cube. And then we all know that we introduce different kind of models which is based on the equations of physics for the simulation purpose of this structure. So I'm including concentration dependent mobility, field dependent mobility, KP model, Fermi model, incomplete recombination model, concentration dependent Shockley-Red Hall recombination model, OJ recombination model, optical band-to-band recombination model, and print model. Print model, by the way, is used if you want to see the parameters of this structure in the runtime output over here as well. Excuse me. Then we can use the output command to look at different output parameters. For example, band.temp is a really useful command. It gives us conduction energy level, valence energy level, and so many other different parameters. So we can use that, excuse me, or we can also use this command for looking at the conduction energy level, or this command for looking at the valence energy level, or for looking at other parameters. Then we can use charge and polarity dependent charges, electron mobility, hole mobility. If we want to look at the Shockley-Red Hall recombination in the solution files, we can include this command. This command is used for the inclusion of radiative recombination parameters in the solution files. Or we can also include this command to look at the OJ recombination parameters in the solution files. Then we can also include permittivity parameter. And a very useful command is flow lines for devices such as diodes, light emitting diodes, solar cells, photodetectors, and other kind of devices. Then for numerical solution, we need to include a method. For this purpose, we are using Newton. Solve initial command is used for initial guess of the structure under thermal equilibrium. Then we save the output file. Let me call it abc.structure. And for plotting this structure, we use the command of Tony plot. And finally, we have already included quit into our code. So after writing this, and I'm going to expect, I'm hopeful, optimistic that we don't have any errors in this file. Let me save this file as well. And desktop, new material. I already have a few files for new material. Let me save it with the name of new material.4. There is some sort of error over here. Oh, okay. So there is a spelling mistake, syntax error. Let me correct it and then run the code once again. Once it gives error, I mean, you have to run it a couple of times then. So now here is our structure, and as you can see that this layer over here is silicon and this layer over here is gallium nitride. We can left click on the structure, then click on display meshing in order to display the meshing. So as you can see that the meshing is denser at the interface of the silicon and gallium nitride layer. Then if you are interested in looking at the energy band diagram and at other parameters around this interface, what we do is we left click on tools, then cut line, and draw a cut line at this interface. Left click on this window at the right. So now over here you see the doping concentrations in these two layers. For the silicon layer, we have defined a doping level of 10 to the power of 18 per centimeter cube, and for the gallium nitride layer we have defined a doping of 5 into 10 to the power of 18 per centimeter cube. So that is obvious. If you want to look at other parameters, we right click on this figure and then click on display, uncheck absolute net doping. For example, I want to see the energy band gap of these two materials. So as you can see that the energy band gap of silicon over here is around 1.1 electron volts, and the energy band gap of gallium nitride over here is around 3.4 electron volts. Let us also look at the conduction energy level, valence energy level, electron quasi-Fermi level, and whole quasi-Fermi level of this structure as well, and then hit apply. So now we see the energy band diagram of this structure. Here the Fermi level is close to the valence band, so this is our p-type layer, and on the right the Fermi energy level is close to the conduction band, so this is our n-type layer. Also we see here our band gap is around 1.1, so this side is silicon, and here the band gap is around 3.4, so this side is gallium nitride. And as it is a heterojunction, for heterojunctions based on the alignment of the energy band gaps, we might have a kink over here. So that kink is also representative of the heterojunction. We can see that over here as well. Now we have already simulated the structure based on built-in materials of silicon and gallium nitride, but at this point I'm more interested in the inclusion of a new material, which is copper oxide in my case, for certain applications for my research. So for that purpose, first what I'm going to do, I'm going to give it a try, and I'm going to replace silicon with copper oxide in this code, and let us call this file for ABCDEF. Let us save it with the name of ABCDEF, and I'm going to give it a try to run it to see if this is going to work. It's not working, it's giving me error. What is the error? In order to see that, let me extend this runtime window. So the error is that it's an unrecognized material its name is copper oxide, but it's unrecognized. So just writing the name of the material is not enough. We have to put in more effort in order to include a new material into Silvaco TCAD. And for that purpose, what we are going to do is we define copper oxide as a user-defined material, user.material in region number 2. And in the next line, we need to define different parameters of this material. For that purpose, we are going to use the command of material. Material is equal to copper oxide. We need to define its user group. So as copper oxide is a semiconductor, so I'm going to define its user group as semiconductor. But we can include metals, which is a conductor, or insulators as well in our for the inclusion of new materials, depending on the material. And then we include another command, which is user.default. So by default, copper oxide is based on, for example, silicon. Most of its properties would match with silicon. So whatever properties do not match silicon, we have to introduce it individually. For example, its band gap is in the range of 1.2 to 2.1 electron volts, depending on different phases of copper oxide. But for the sake of example, let us assume that the band gap of this copper oxide material is 1.5 electron volts. Then we can include other parameters as well. For example, the electron recombination lifetime, we can set it to 1e-7 or 0.1 microseconds. Similarly, the whole recombination lifetime can also be set to 1e-7. Mobilities can also be set. Assume that the electron mobility for copper oxide is 1000 centimeters square per volt second, and the whole mobility for this is 500 centimeters square per volt second. This is just assumption. You can look at literature and include the actual parameters for this material. Similarly, we can set permittivity to a specific value as well for the copper oxide material. Now this completes the inclusion of a new material. So as you can see that it's really easy to include a new material. It's just going to require a couple of lines to include the new material. And this new material is included in region number 2, and we have also defined doping for region number 2, which is p-type. Generally, by the way, copper oxide is inherently it's p-type. So we have to take care of that, take into account those kind of factors as well. And after this, I'm going to give it a try to run the simulation once again. Success! We are able to run the simulation. This blue region over here is copper oxide, and this region over here is gallium nitride. So now I want to see the band gaps at the interface of these two materials. So for that purpose, we click on Tools, Cut Line, draw a cut line at the interface, hit OK, then left click on this window. As we see that the doping concentration in the copper oxide layer is 10 to the power of 18, while in the gallium nitride layer the doping level is 5 10 to the power of 18 per centimeter cube. We can also look at the energy band gaps across this interface. So it is 1.5 electron volts for copper oxide and 3.4 electron volts for gallium nitride. Similarly, we can look at conduction energy level, valence energy level, electron quasi-Fermi level, and hole quasi-Fermi level. Since we are looking at the structure under thermal equilibrium, so the electron and hole quasi-Fermi levels would be the same. And here is our energy band diagram. So this is how we include new materials into Silvaco TCAD software. We can include new material into different kind of devices. This is just a simple structure, but you can include it into PIN diodes, LEDs, solar cells, photodetectors, etc. And then we can look at the current voltage characteristics of those devices as well. That concludes the session for today, and I hope to see you next time. Till then, take care. Bye.